Start off from where we left in the last class, which was we are doing the diffusion reaction model, if you remember. So let me go back a little bit and try to show you what we are doing. So this was what we are looking at, a matrix, an immobilized matrix which is insoluble in water, and on this the enzymes are attached covalently as the receptors, and these red dots set here are the enzymes, Re being the radius of the enzyme matrix, dE being the diffusivity of the matrix. So this is what we are looking at. Now what we wanted to do, we wanted to model the system and try and understand how this process of transport and reaction was occurring. So what did we decide? We decided that the diffusion is occurring from anywhere in the solution to the surface of the enzyme, and reaction is occurring at the surface of the enzyme, right. So the reaction is a surface reaction essentially, and because the enzymes are kind of rooted or kind of fixed to the surface, so the reaction would occur at the surface of the enzyme, and the rate of reaction equals the rate of diffusion, mass flux through diffusion at the interface. So it is a simple model. So let's go to the so what we did was, just some of you were not there, then just as a wrap up on that and some summary on that. So the problem that we face here in these, when we talk about immobilized enzymes, is that these are diffusion reaction systems. So diffusion and reaction, or convection and reaction. So some kind of mass transfer and reaction are occurring simultaneously in these enzymes. So it's much harder when you're trying to actually solve the equations of transport and reaction in these enzymes. It's much harder because it's a simultaneous diffusion reaction or convection reaction problem, unlike before in the soluble case where it's simply a reaction problem. Now this will essentially lead, so this what we are doing now, immobilized enzyme, will essentially lead to ODs or PDs to be solved. Now the problem is that the reaction kinetics of the enzyme is what you see on the screen here. It's Michaelis-Menten kinetics, that is the reaction kinetics of the enzyme. Now this is inherently nonlinear. So if you want to solve a set of ODs or PDs with nonlinear terms, you cannot do it analytically, and we cannot do it in the as a part of the course. So what we do is, we do what we did, one of the things that we did before, which was to look at the two extreme ends of the problem, which is the two asymptotes of the problem, which is the very small value of Cs, where the system is follows the first order kinetics, and a very large value of Cs, where the system follows a second or zeroth order kinetics. Okay, so what's the advantage? The advantage is that the actual order, the real order of the system, is a fractional order between 0 and 1, and if we can specify, or you can find the two boundaries or the two bounds of the solution. So your real solution is going to be bounded by these two solutions. So if we can find out the two bounds of the solution between the zeroth order and the first order, we are sort of in business. So that is what we are trying to do, and most of the problems that we are going to solve here, we are going to solve it first using zeroth order kinetics or first order kinetics, and then using zeroth order kinetics, and we understand that our real kinetics and real solution lies between these two. So our actual solution will be bounded by the two solutions that we get over here. So that is the strategy that we will follow. Now if you want to do these on your own with the real kinetics, what you have to do is simply go and solve this numerically, right. So the diffusion reaction model is what we looked at. Now I went and talked about the diffusion reaction model in the Cartesian and the spherical and the cylindrical coordinates. So here what we take is, we take a matrix which is cylindrical. So the diffusion reaction equation is in the cylindrical coordinate. To remind you one more time, we are not solving inside the cylindrical spherical matrix. This is in the spherical coordinate, I am sorry. So we are not solving inside the spherical matrix, to remind you one more time. We are solving outside the spherical matrix. Now then, why do we take a spherical coordinate? We can take any coordinate for the matter, for the for the sake of the, for what? For the sake of the, for the sake of simplicity of what? With respect to what? Why is the spherical coordinate is not simple? The Cartesian coordinate is a lot simpler than spherical. So we could have gone for a Cartesian coordinate, but we go for a spherical coordinate. Why do we do that?
Simply to solve the equation.
Yeah, but which point? At what point does it make it simple? Which part? It is not easier, look at the spherical coordinate equation. So, the spherical coordinate equation is not any easier if I had taken a diffusion times del 2 C del x square or del 1 over r del r of r del C del r.
Only have one parameter, it's not partials.
No, but if we took Cartesian will be two coordinates. That's one thing, that's correct. But you can also take just normal to the surface, that kind of thing, just one kind of yes, but you are in the right direction, but that is not the point. I mentioned this in the last class. It is for the sake of simplicity of the boundary condition. See, the boundary is spherical. See, that is something you have to realize, that the sphere is like the matrix is a sphere like this, and the reaction is occurring on the boundary, on the surface of the sphere, and the surface of the sphere is it is a spherical surface, right. So, as a result of which the boundary condition is on a spherical surface. Now, if you can take any geometry outside in the fluid if you want, but when it comes to the boundary condition, if you have a spherical boundary condition, a spherical coordinate, it helps with the spherical boundary condition. Otherwise, you have to transform from a spherical boundary condition to a Cartesian boundary condition, which makes life a lot more difficult. So, that is why we take this form. Now, the boundary conditions, as we discussed, one is the flux equals reaction rate. So, this is we are doing at the limit of small substrate concentration, where as a result of which the reaction rate is first order, and the other boundary condition is that far away from the matrix, very far away from the matrix, the concentration is a constant. Okay. So, this is where we stop. Now, we go on, and what I want you to do again is to put your pen to your paper and try and quickly solve this, integrate it first, and then put your boundary conditions in there and see what you get. So, this is the equation that you need to solve. Just integrate it very quickly first time. So, if you integrate it first time, you get r squared del dCs dr equals constant, right. Can you obtain the value of the constant right this step? No, because you have a what kind of boundary condition? One is a Dirichlet boundary condition, fine. The other one is a Robin's boundary condition. Yeah, mixed or Robin's boundary condition. So, you cannot get dCdr at initially right away. You need to solve the whole thing, and which is what we are trying to do. So, Cs is something like this, you get. So, Cs this is what you get. Okay. Now, use the second boundary condition, r going to infinity, Cs equals Cs naught, which means that Cs means A2 equals Cs naught. So, Cs minus Cs naught equals minus A1 over r, and so A1 equals you get that after using the first boundary. So, you use the second boundary condition, get your Cs minus Cs naught as this, and then you plug this back into the first boundary condition. Okay. So, if you forgot, then your del dCs del R equals A1 over R, R square, sorry. Fine. So, then you can put this back from here, which is that A1 equals minus CS minus CS naught over R, right. So, R fine. Then you can just use this boundary condition at R equals RE. Fine. So, let us go to the screen and I have the solution for you. So, this is the final solution that you have, which is CS equals CS naught times 1 minus K1 RE over R over this denominator. You get that, or is too quick? Okay, just make a note even if it's a little quick. So, up to this is fine, right? Up to this is fine. All you need to do is now replace this into the first boundary condition and just do a little bit of algebraic manipulation. So, now you get your CS as CS naught times this number. Okay. So, what are we trying to find here? You know, those of you who are there in the last class, one of the major aims is trying to quantify the reaction rate. What reaction rate? Which reaction rate? Yeah, the observed reaction rate. Okay, the intrinsic reaction rate could be different, but there is an observed reaction rate, not the surface reaction rate, but an observed reaction rate. Okay. So, observed reaction rate or observed flux is equal to observed rate of surface substrate reaction. Okay. So, this is my observed rate of flux, which is minus 4 RE square times ds del CS del R or dCS del dr at R equals RE. Fine. Is it clear with everybody? So, that you can, because you calculated that your R times dCS dr, just now we calculated R times dCS dr equals A1. Okay. So, you can put that constant from there, and A1 we got as here this. Okay. Just now we got this, that R times dCS R times dCS dr equals A1 over R, sorry, and so you can put that over here. So, R square times dCS dr equals A1. So, this you are trying to evaluate at R equals RE, right. So, you get RE square times dCS dr equals A1. So, 4 pi ds is there times simply times A1. So, we have calculated what A1 is. So, you can put that back over here and this is what you get. Is it clear to everybody, that little algebra? Now, what is this trying to show here? This is, see, in ideal case, if you did not have mass transfer limitations, what would your reaction rate be? It simply should be K1 into CS naught, right. So, K1 into CS naught. But what this is showing is that, look at this number over there, the denominator is larger than the numerator. So, this is a fraction. Okay. So, what this is showing is this is smaller than K1, and why is it smaller? Because of the mass transfer limitations, right. Is that clear to everybody, Lisa? So, that is what we are trying to achieve. So, all these calculations we are trying to achieve what is my actual reaction rate. So, that you can have an intrinsic reaction rate, which is the ideal reaction rate that you would like to have over there, but then life is not ideal, and you know the reaction rate that you get over there is not the ideal reaction rate, it is lesser than that, and that is called the observed reaction rate. And what we are trying to calculate here is how much less is the observed reaction rate than the actual reaction rate. So, this is what we get. Now, if you look at this, what we can do is we can take an inverse of this. Okay. The reason is that, so I can write it as K observed times CS naught. Now, if what would my 1 over K observed be? 1 over k observed would be 1 over, yeah. So, you take the inverse of this. So, do you see what I am trying to approach at? Right. So, 1 over k observed equals 1 over k 1 plus 1 over pi ds R e. Now, 1 over k 1 is a which resistance? Reaction resistance for the simple reaction, and 1 over 4 pi ds R e is a mass transfer resistance. So, yes, so this is one of the cases. I am not sure if you have done such an example before, where you have done examples where reaction two say mass transfer resistances or 2 heat transfer resistances are in series, but I am not sure if you have done a case where 1 heat transfer resistance or 1 mass transfer resistance is coupled with a reactive resistance. Okay. So, if you have, then it is an interesting thing. Otherwise, this is one of the examples where you look at that is it is called reaction in series, but the only difference is that the reactions resistance is in series, but the only difference is that the 2 resistances or 3 resistances we are considering are not necessarily of the same type. So, you have a reactive resistance out here and a mass transfer resistance, and you are adding them up to get your total resistance. Okay. Now, so this is the reaction is controlled. So, this is an intermediate. So, if you go, let me go back to that slide. Here. So, the observed rate of reaction we decided could be same as the intrinsic rate of reaction if the system is diffusion limited, could be same as the rate of diffusional transport if the system is diffusion limited, and could be intermediate, that is depending both on reaction rate and diffusional rate if it is in the intermediate regime. So, it turns out that for this particular case, where what we are doing here, it is in the intermediate regime, and as a result the reaction is controlled both by the observed reaction, so to say, is controlled both by the intrinsic reaction and the mass transfer, and the total resistance that you get in the system is a combination of these 2 resistances. Now, when I say combination, it could be different kinds of combination, and one of the things that you have to understand very clearly is that why do we get resistances in series? Can you tell me? Why are these resistances necessarily in series over here?
First, the diffusion occurs means the substrates
right, and then
to the surface.
So, first the diffusion occurs and then the reaction occurs, right, that is the right answer. So, see, the resistances or the way you write your mathematics is only governed by the process. So, when you say that the resistances are in series, it automatically means it should hark back to the fact that the processes are in series. That is the point. It is not that it is not God's gift to biochemical engineering that all resistances are going to be in series all the time. They need not be in series, but it is that the processes are in series, which is what he said just now, that first the diffusion occurs and then it is followed by the reaction. As a result, resistance is in series. Why I am trying to tell you this is I am trying to impress upon you the fact that do not close your eyes and write resistances in series all the time. Try and see if the processes are in series. Now, this is a very this is an effort saving exercise, that if you understand whether the processes are in series or not, then you can figure out what the resistances are and you can write down the total resistance right away without doing all these calculations. You see, once we do the calculations, we try and want to come out with a conclusion that we can use in a generic way. So, but you can skip the calculation provided you are right with the physics. Okay. So, if the resistances, if the processes are in series, the resistances could be in series A, and B is that you have to also check what kind of coordinate system you are working at. So, even if the resistances are in series, the way they would look in a Cartesian coordinate is different from the way they would look in a cylindrical coordinate, is different from the way they would look in a spherical coordinate. So, these 2 things you have to keep in mind when you use this. One is check the process. If they are in series, then you can use the resistances in series concept, and then next check the coordinate system and then use this. Okay. So, that is one thing we want to do. Now, what I want to do is do the other limit. So, we did the limit of the small concentration, which gives you first order kinetics. Now, let us do the limit of the large concentration, which will give you a 0th order kinetics, and this is very straightforward. So, in 0th order kinetics, what happens is the reaction rate is a constant. Okay. And so, the reaction rate is constant equals R max, and let us just represent that by k max. The reason is because we just want it to be in terms of a rate constant. So, what would be my governing equation now? It is still the same, which is, can you write that? Do you remember to write that? What is it? Still in the spherical coordinate, and what is the governing equation? ds by r square ddr of r square ds dcs dr equals 0. Yeah. So, what would be my, that is my governing equation. Boundary condition 1 would be at r equals re, what is my boundary condition? 4 pi 4 pi re square ds into del cs del r equals, that is the only difference now, equals k max. And BC2 would be simple, same, at r going to infinity, Cs equals Cs naught. Now, you can quickly solve, is the same thing. So, Cs equals Cs naught plus A1 Cs naught minus A1 over R, I think that is what you will get. So, Cs equals Cs naught minus A1 over R, and so dCs dr equals A1 over R square. So, 4 pi Re square ds dCs dr equals, this equals minus 4 pi ds into A1, right. This is what you got, which equals k max. So, A1 equals minus k max over 4 pi ds. I think there is a sign thing. So, this should be plus, huh? This should be minus, I think, and that this should be plus here. So, Cs equals C naught minus k max over 4 pi ds over R. Done. So, this is what we wanted, we want the profile, and then you have to calculate the flux, right. So, so what would you get for the flux? I mean, this is a back calculation, but you would still get the same thing, 4 pi Re square ds times del Cs del R equals Re equals 4 pi Re square ds times over Re square into that is about it, I think, 4 pi ds to k max and over Bs, right. So we feel kind of shortchanged, right? After doing all the analysis, we kind of feel shortchanged. Why? Because we started with this. This was one of our boundary conditions. Do you see what I'm saying? So if you go to the screen, let's look at this boundary condition out here. Okay. So this was our boundary condition anyway. So what is here that is going on? What is going on here? You know, there's the inherent physics that is there. You know,
all the receptors are associated with enzymes.
No, that's not the point. Yeah, all the receptors could be associated with enzymes, but that's not the point. You know, there's something going on here. You have to, you know, you do the calculation, then you figure out that, as I said, you kind of feel shortchanged, and you thought that, well, this was what was given to us, and why did we have to do all this and come back to the same thing? But the reason we did this is because there is a slight physics of the problem that we didn't address at the beginning. If we thought about it, then we probably wouldn't do this exercise, because it's kind of redundant. And what is that? I want you to, after having done that, I want you to go back and figure it out for me. It's right there, you know, whatever, if you look at the screen and whatever the equation is on the screen, it's there in that equation. You just have to read it off there. What does this thing mean? This or here or whatever. What does boundary condition mean? No, reaction rate is always equal to flux. That was there before also, but what is so specific or special about this one?
This time reaction rate is not depending on conservation, it's constant.
Yes, that's right. What does that mean? What does it imply?
Zero order.
I know it's zero order, but what does that mean imply?
We don't have reaction resistance.
Yeah, that means that we do not have reactive resistance, or in other words, at any point of time there is enough amount of substrate. What does a zeroth order mean? Zeroth order is, you know, I told you this before, there is no reaction such as zeroth order. You know, reaction cannot be zeroth order. Reaction is first order, second order, fractional order. So zeroth order is a concept, it's not a reality. So that's what I'm trying to say. So when you say it's a zeroth order reaction, it doesn't mean anything. It's a concept. So what does that concept mean? That zeroth order concept means that at any point of time there is so much substrate at the reaction site that it is independent of the substrate concentration. Okay, you see what I am saying? That does not mean that the reaction is zeroth order actually. It does not mean that the reaction is actually independent of concentration, because how would reaction occur? I mean, this is something that we discussed in the first or the second lecture. How would the reaction occur if there is no substrate? Can you just make reaction happen without substrate? No, you cannot do that. So it is not possible to have reaction without substrate. When you say the reaction is zeroth order, you mean that there is so much substrate at the reaction site that it is not inhibited or limited by substrate at any point of time. Okay, that is when it means zeroth order. So which means that it could be actually a first order reaction, for example here, or any other order reaction, but if the amount of substrate is enough and it is a constant at the reaction site, then that can be absorbed in the K. You see what I am saying? That is mathematically speaking, that is the idea, that if there is enough of reactant at the reaction site and so much of reactant that at any point of time it is more or less constant. Like if you need 1 millimolar of reactant at the interface or for reaction, and if you have 1 molar of reactant there, and if you have 2 molar, if you have 10 molar, it does not matter. For the reactant which equals 1 millimolar, 100 millimolar or 1 molar or 2 molar is still the same. So you can absorb all of that, because then it becomes like a constant. You can absorb all of that in the rate constant and get that. Now, what happens over here is that so there is enough reactant that is there at the site. As a result, whether there are mass transfer limitations in the system or not. Actually, well, you didn't say it right, and I didn't. Yeah, I should have agreed with you that point. So we will come back to this. So whether or not there are mass transfer limitations in the system does not make a difference. Okay. So the only thing that matters is just the opposite. The only thing that matters is the reaction resistance. So the only resistance that's there is reaction resistance. So my K observed is going to be equal to K max. Okay. So let's go quickly. Yeah. So my K observed equals K max. So there is no diffusional or mass transfer resistance in the system at all. Is it clear? So this what we did is gives us a way of understanding more fundamental mechanism of what really happens when there is when you say it is a zeroth order reaction, which is that the mass transfer resistance, as soon as you say it is zeroth order, which it means that you are supplying enough reactant to the reaction site, and the only way you can supply enough reactant to the reaction site is when you are overcoming the mass transfer resistance at a steady rate. And the only way you can overcome the mass transfer resistance at a steady rate is when the mass transfer resistance is very much smaller as compared to the reactive resistance. So here there is no mass transfer resistance, as a result your K observed equals K max. Okay. Is that clear? Is there any question? Is there any question on this? On what we did? So we are going to next topic, but before we do that, if there is any question I will address. None? Shall we move on? Okay. So the next thing that we are going to do is interface mass transfer between enzyme receptors and substrate dissolved in a moving fluid. So the major difference is, in the first part that we did, we only considered diffusion and no movement of the fluid. So it was as if a static fluid was there and the enzyme matrix insoluble in it is dropped in it and the diffusion and the reaction occurs. Okay. Here what we are going to do is we are going to look at moving fluids. So for example, if this is an enzyme and there's fluid this enzyme is in your gut, for example, some kind of enzyme, digestive pill or something that you have taken, and it's on your in your gut, for example, and the fluid that is there in the gut, it's moving, right? You're drinking water and so on. So there is movement of fluid in your gut. As a result, there will be convective effects now. So that is the added complexity that we add in at this point, and we do not include so much of diffusion in there, because the convective effects, you can include diffusion of course, but typically the convective effects will always outweigh the diffusive effects, but of course you can include diffusion. So if you look at this picture over here, this is now the matrix, the one with the cross signs over here, this is the matrix of the enzyme on which the enzyme is kind of attached covalently here. So these are the receptors and these are the enzymes, and the fluid that you have is flowing in this direction, and you have the x and the y coordinates. Okay. So the enzyme, so what is happening here, that the enzyme substrate binding at the interface of the matrix and the solution obey first order. As I said, that is again an asymptote of the whole problem. So what I want you to do is, so there are two ways of solving it, or maybe one way, but one way coupled with another way, which is the convection diffusion reaction equation. Okay. And the next thing that you have to do is to include the concept of the mass transfer coefficient. Okay. So if you have to write, so first let me ask you, so where are you going to use the convection diffusion reaction equation first of all? It will be in the boundary condition, that is correct. So where are you going to write the convection diffusion equation then?
In the boundary layer.
In the boundary layer, right. So this is your solid. So this goes back to the classical boundary layer problem. This is your solid. This is the liquid fluid that is coming in, and you have a boundary layer that is created. And so you have to write not a convection diffusion reaction equation, but a convection diffusion equation with a reaction at the boundary condition. We can still call it a CDR or a convection, because it is still convection, diffusion and reaction, all three are there. It is still called a convection diffusion reaction equation, but the reaction is not going to be in the governing equation, the reaction is going to be in the boundary layer, fine, and you can solve it. The problem with solving it is it is little complicated, and there are solutions possible for it, and it is slightly complicated. The other option is the option of mass transfer coefficient. So we can use a mass transfer coefficient. So if you know what the mass transfer mass transfer rate is from the fluid to the solid, then you can use a mass transfer coefficient, and in that case what would be your basic concept? At any point of time, that is anywhere your basic concept, that that what are the two rates that are equal at the interface? Yeah. So, the mass transfer, whatever is coming in because of mass transfer from the fluid into the solid equals what is reacting on the solid interface, is that right? So, if you look here, so whatever is coming in from here to here at this interface equals what is reacting. So, what I want you to do is, now first can you write from what you studied the Cdr equation? So, let me try and help you. Yes. So, this is your solid, okay, and so which direction the main velocity is? In the y direction, let us say, okay. Or shall we call, maybe we should call this, let us call this x and this y, okay. That is what is done classically. So, if you write the convection and diffusion equation, there will be two components, of course, the convection and the diffusion, right. So, this is a fluid, for example. And the enzymes are here. So, what would be the terms, diffusion terms, say?
Diffusion term is only ds into del C and del X.
Okay. And
Convection term is Vx into del C del X.
V?
Vx into del C del X.
You said ds into del 2c del y square, right? Okay. And well, I would, why not this term as well? There is no reason for it not to be there.
We can neglect this in the exhaustion.
You can neglect this term using scaling analysis in this direction, and
This will be very insignificant as convection.
yeah, that is what we said initially, that when you have convection, the diffusion terms, one of the diffusion terms you can neglect. So, that is a possibility that you can neglect this term, and then if you neglect this, then d2 as so. Okay. So, do you know how to solve this?
By assuming Vx by Ky or something.
Yeah, but Vx in the boundary layer is going to be a function of y, right? Vx in the boundary layer is going to be a function of y. So, if it's a fully developed flow. So, you can go back to the boundary layer theory and try to solve this, and then at the boundaries you have to use the boundary conditions. Okay. So, what kind of boundary conditions would that be?
So, mixed boundary.
Yeah, at x equals at this surface y equals 0. So, y equals 0, you will have what you will have minus ds del c del y equals so some k double prime equals into c or something, and x equals
0. It will be initial CS1.
yeah,
C equals to CS1.
c equals cs naught or something, and similarly at y outside the boundary layer, okay, y equals to delta. So, this would be your, these two would be your boundary conditions. Okay, fine. So, you can just go ahead and solve this. We are not doing this exercise in the class today. So, you can go ahead and solve this. What we will do is we will just use the straightforward concept of mass transfer coefficient, excuse me. So, this is what you do, straightforward concept of mass transfer coefficient, and do this. There is a slight error here, there should be ds times del cs del y equals k double prime. Now, why do I use k double prime?
It's not
rate at the surface. So, K double prime is typically used for surface reaction rate, and K triple prime or Kv is used as a, so Ks or K triple prime is for a volumetric reaction rate. Okay. So, this double prime corresponds to the 2D and triple prime corresponds to 3D. So, other boundary conditions are the same as the boundary layer problem. So, the second method that we can use is a method using mass transfer coefficients, which is that you assume a mass transfer coefficient and the rate of mass transfer equals the rate of reaction. It is a very straightforward concept. Okay. So, this is what you do here, it is on your screen. So, and y at y equals 0, and y at y equals 0 equals some Kf into Cs naught minus Cs equals K double prime into Cs. Okay. Very straightforward. That so, whatever is your outside the boundary layer, whatever is the concentration minus. So, then through the mass transfer coefficient you substitute the boundary layer concept at all completely, right. So, you just substitute the whole concept of boundary layer, that is Cs naught minus Cs, whatever is the difference between outside the boundary layer and at the surface, times the mass transfer coefficient for the boundary layer equals what is being consumed at the interface. So, if you do that, then you can directly, so from this for example, you can directly Kf times Cs naught equals K double prime plus Kf times Cs, which implies that Cs equals K double prime plus Kf over Kf. That is fine. So, this is what you get, and once you get that, so what does it mean now? Your reaction rate at the surface is what? Is K double prime times Cs, fine. So, Kf, did I? I think Cs naught equals this times Cs. So, Cs naught equals this times Cs. So, Cs equals Kf over and Cs naught, fine. So, your reaction rate is this. So, R equals R double prime, let us call that, equals K double prime times Cs equals K double prime into Kf over K double prime plus Kf into Cs naught, fine, which means that if you take an inverse again, so this is my K observed times Cs naught, fine. So, K observed equals K double prime Kf over K double prime plus Kf, or 1 over K observed equals is it right? So, you again figure out that resistances are in series. So, whether it is diffusion or convection does not matter, as long as the processes are in series, you can always add up resistances. Okay. So, just a quick time scale analysis we will do. These are things that we already did. So, no point going through them again. So, this is what we find, that 1 over K observed is 1 over Kf plus 1 over K double prime, and therefore, the total resistance is summation of the reactive resistance and the mass transfer resistance. Okay. So, just after having done all this, let us have a quick look at the time scales that are there in the process. What did we do in the last class? Last class we did the time scales that were in the concerned time scales of that are there in the system. What were the two time scales? The time scales of diffusion and the time scales of reaction, right. And can you go back to your notes and just look, what we did was the reaction time scale was C naught over R C naught, the diffusion time scale was L square over d m, and then we got the fees T d over T r, I think we got, right, L square R C naught over d m C naught d m, right. Is that what we got? This is my Thiele modulus, right. So, for phi square much less than 1, it implies that T d much smaller than T r, and the system is reaction limited, right. For phi square much greater than 1, T d is much greater than T r, and system is mass transfer or diffusion limited. Okay. Now, phi square is a Thiele modulus, which is the ratio of diffusion time to reaction time. What we have to do today, after this analysis, is slightly change this. Why? Because the governing processes there were diffusion and reaction. The governing processes, the main dominant governing processes here are convection and reaction. Okay. So, we have to, the time scales that are involved would be slightly different time scales, and we have to come up with a different dimensionless number. So, Thiele modulus is a dimensionless number. It is a very important dimensionless number actually, and we will come up with another dimensionless number. Can any of you guess what the new dimensionless number is going to be? Yeah, that is going to be the number. So, here what we do is the mass transfer resistance is L over K f, and the reaction resistance is L over K double prime. Why is that? Why is the L coming in here? Because it is a surface rate. Okay. So, just to consider, take that into account, and if you remember, my mass transfer coefficient and K double prime, they have the same units, right. So, just to make this the unit of time, so mass transfer coefficient, mass transfer time scale is L over K f, and the reaction time scale is L over K prime. So, my T m same way, T m over T r equals L over K f over L over K double prime. So, that is K double prime, and that is my So, Damkohler, it is named after Damkohler, who is a very famous German scientist, probably the most famous chemical reaction engineer ever, and his seminal paper was Damkohler seminal. So, his name is I think, if I remember it right, Gerard Damkohler, and his seminal paper is in 1937. Okay. His major contributions are in this paper. This is probably the most famous paper ever written in chemical reaction engineering. Unfortunately, it was in German in that point of time, and it took many years for that paper to be translated. And so, his main contribution is, the most important contribution is the Cdr equation. So, he is the one who wrote the Cdr equation, that equation that we write over here all the time, ds times Laplacian of C equals R of S or something. So, that equation that we write, and he is the first one who wrote. He wrote it in the x, y, z coordinates. So, ds del 2 c del x square plus del z square equals R v, and if you come to think of it, in 1937 to write something like that was a big deal. because it's not just writing an equation, it is bringing together the concepts that are embedded in that equation. So, he was the first one who wrote the Cdr equation. He was the first one who also wrote or maybe the second one after Langmuir. Langmuir is the first chemical engineer to get the Nobel Prize. So, Langmuir wrote it slightly before that, but he wrote the one which is known as the Danckwerts boundary condition. And I wrote a whole paper just on the history of this chemical reaction engineering and how it evolved all the way from the 18th century. So, at some point of time I can share that with you, but so all that is written there with the details of which year, who discovered which boundary condition. So, this is the mixed boundary condition that we use all the time. So, minus ds del 2s del x equals v times c minus c naught at x equals 0. So, at the boundary of the reactor or the plate, when both convection and diffusion are there, this is what you use, that is the del c del x, the diffusion term equals the velocity times the difference in concentration. So, this was also founded by Damkohler. So, it is no wonder that the most important number in whole of chemical reaction engineering is named after Damkohler, and so these were his two major concepts, and he brought in some other concepts. It's a great paper, and one of my colleagues who is a German helped me translate. I mean, he translated this paper for me, and so it's a very long paper, but it's a great paper. So, if you look at the screen now, so without further ado, because we are running out of time. So, our reaction rate equals Cs naught. Why is that? Because if I look back, my reaction rate was given by, so K observed equals K double prime Kf over K double prime plus Kf. Okay. So, my R equals K observed times Cs naught, which is K double equals, so K double prime over 1 plus dA times Cs naught, right. So, in this, if dA is much less than 1, then my R double prime goes to K double prime Cs naught. Is that clear? So, what is this now? This is reaction limited, right. Why is it reaction limited? Because the reaction rate that you get over here is same as the reaction rate in the absence of mass transfer, which reaction limited means very little mass transfer resistance. So, and let us look at the other end. So, just to summarize, so dA much less than 1 minus R prime equals K double prime Cs naught. So, reaction limited, and dA much greater than 1, then your minus R double prime equals Kf Cs naught, Kf, right, because if this much greater, then you take the inverse of that, and take the limit, because here if you look here, you cannot take the limit directly. Okay, this will so basically what you have to do is put this over here. So, you will have K double prime over dA, okay, and then substitute back in that. So, K double prime over dA, and then dA equals Kf over K double prime over Kf, and then you will get Kf over Cs, Kf Cs naught, fine. So, this will be your mass transfer limited regime, which means that reaction resistance much smaller than mass transfer resistance. Because we had defined, the way we had defined our Damkohler number is my mass transfer time over reaction time. Okay. So, let me put this over here. So, the way we defined our Damkohler number is mass transfer time over reaction time. So, if my Damkohler number is very large, it means that mass transfer time is large, and if it's very small, then the reaction time is large. So this is reaction rate over mass transfer rate. Is it clear? Okay. Let me write it clearly here. So Damkohler number equals mass transfer rate time over reaction time equals reaction rate over mass transfer rate. So if my Damkohler number is much greater than 1, it means that reaction much faster than mass transfer. If this is much less than 1, it means mass transfer much faster than reaction. Right? So based on this, we can get the two asymptotes of mass transfer limitations and reaction limitations. So I think we'll stop here, and we'll continue with the mass transfer coefficients at different flows, and then looking at interphase mass transfer in next week's lectures. So thank you.